Welcome back, boys and girls. We're in the lab today, and this is what should probably have been my first electronics video. But what is it? It's the second. Anyway, we're going to get into it finally. Electronics. And I've had several friends and colleagues, fellow ham radio operators and the like, who have been saying, you really gotta get to the electronics. Well, this is what I do. Machining and fabrication is a hobby. It's a basis for cobbling things together and making stuff and doing prototypes. But electronics is what I do. It's what I'm trained for, and it's how I made my living. And I spent most of that living in laboratory environments, doing a lot of laboratory calibration and interfacing. I've seen all kinds of. I started in design, electronic design, which I really like, and I still enjoy. The technology has gotten away from me a little bit. I haven't exactly kept up with all the changes, but we've gotten into the surface mount and that sort of thing. So this is going to be a little more serious in terms of what I'm presenting to you. This is not going to be a basic electronics stuff. I'm going to make the assumption that you are, if you're getting your hands into modern solid-state radio, transceivers, that you know enough about electronics to know whether or not you should have your hands in it. And if you know that much, then I can talk to you on that level. I will go through some basic system training on just how to think your way through a problem. These radios, all these electronic devices today, they're fairly complex. The electronics of radio hasn't really changed much. Some of the devices and techniques, the integrated balance modulators and things of that nature have changed things slightly, but basically that's all the same. The control systems have gotten a lot more complex though. The proprietary chipsets, digital controls, phase lock loop, multiple overlapping phase lock loops can quickly become confusing and overwhelming if you're trying to troubleshoot, which came first, the chicken or the egg. I mean, we're dealing with a lot of feedback systems here, and it's a loop. And if the loop's not working right, you need to determine why. Sometimes that's difficult without breaking the loop. So I'm going to get into all of this sort of stuff, and we'll try to simplify whenever we can, and then build on those concepts. But I'm going to tell you first off a couple of things that need to be remembered and applied. And I don't care whether you're playing around with a simple little code key oscillator, or the latest and greatest, Yaesu FT, whatever they've got out there now with all the bells and whistles. I'm not really into solid state radio. Solid state, software defined radio. So we're not going to be playing around with any of that. So anyway, the first rule of thumb is, I don't know, first or second. Maybe the first. The first rule of thumb is, it's been my experience that 95% or more of all electronic problems are freaking connectors. And I say that with that emphasis because they are just the bugaboo. Connectors are, they never seem adequate. If you need a 10 amp connector, you probably should be using a 30. I mean, they're just awful. The A good gold-plated connector with lots of surface contact area is, obviously your best bet. And that's rarely what you get to work with. Usually it's some sort of, tin plate, CAD plate, whatever. And the contact surface area is, if you've got 10 or 15% of true metal-to-metal contact in a connector, you're probably ahead of the game. And the spring tension, the actual contact pressure, is usually not very much, especially if you're dealing with a multi-connector with lots of contacts. If you had really adequate contact pressure on every contact, you couldn't put the thing in and out. You couldn't plug it in and out. It would just, the forces would be so great. So contacts are always a problem. So they need to be clean. You can polish them up with a little a Q-tip and some rubbing alcohol or something along those lines. If you need something more abrasive, maybe a brass or a metal. I don't like steel brushes, but little brass brushes. Anything to get the surface corrosion off. Don't go spraying, blue stuff or deoxit or anything through your radio. I mean, I know a lot of people advocate that. It's not a good idea. If you want to use an electronics cleaner, use a, quick evaporating, I got some here, electronic cleaner, something that evaporates, it's clean, doesn't leave a residue. If you feel you absolutely need to put something on a set of contacts, whether it's an edge card connector or what have you, but you feel that it's in an environment where it's going to be subject to moisture and you just want to give it a little surface protection, I like silicone grease. A thin film of silicone grease is usually works pretty well. If it's a real high current connection, like the 20 amp power connection between your not this end of it, but you've all seen these these 20 amp 4-wire ribbons on the the Asus ICOMs, Kenwoods, what have you. At the terminal end where it's screwed to your fuse block or power supply or whatever, I like something called copper weld. That's antenna wire. Copper shield. KOPR shield. Copper shield. It's made by Allen Bradley. It's a non-acidifying, very stable, highly refined grease, which is laden with copper, finely ground copper. You can also use Never-Seez. The real Never-Seez uses nickel. I think Permatech, I don't know about Permatech, I'm not sure about their version of Never-Seez, but I believe the Permatechs and some other brands use aluminum. Don't use that. You don't want the aluminum. But a metal bearing grease for high current connections, silicon or a silicon dielectric grease for everything else, including coax connectors. I said in another video, and I'll say it again, the best way to keep moisture out of a connection is not to wrap it with all kinds of voodoo tape and sealants and goop. The best way to keep anything out of a connection is to fill that connection with something else, preferably something that is that abhors moisture. A good dielectric grease, fill that connector up, screw it together, you're done. That doesn't mean water won't migrate into the coax and contaminate the shield and the dielectric and all of that. But when you take that connector apart, it'll be clean. And that's important because that's a connection. The problem with connections is when they do begin to fail, even before they actually go open, they start to become nonlinear. They start to react like a diode. And for radio applications, that's awful. I mean, you start to create, tremendous amounts of harmonics. The antenna connections where the tubing slides together in aluminum radio antennas. You start to get diodes in those after a few years of being up in the weather, and all of a sudden the neighbors are complaining about TVI and whatever. Though nobody uses TV antennas anymore, so it doesn't really matter. But you get my point. Rectification, not good, not a good thing. In repeater sites, I could tell you stories about rectification at repeater sites in every piece of metal in the environment, including the building structure. But we won't go there today. Okay, so connections. Connections basically suck. Always be suspect of your connections. Wiggle things, touch things, poke things, prod things while they're alive, active, receive, transmit, whatever. I like to use, I have fiberglass and bamboo chopsticks. Work very well. Chopsticks, by the way, can be carved to make tuning tools and all kinds of things. I'll go over equipment and tools and stuff in a moment. I may never get to this radio. I got a TS440 here that we're gonna go through. It's got VCO issues, I believe, which is nice to know what the problem is, but we'll still get into some troubleshooting technique. Okay, so connections. I could go on and on about connections. I'll bring it up again as opportunities arise. So yeah, poke things, prod things. A lot of times you'll find the problem is simply a connection. Anything that's spring-loaded, fuse connections, contacts. If they get hot, the springs weaken. Even the best beryllium copper will lose its tensile strength if it gets annealed from current heating. Okay, moving on. Rule number 2, and this is really important, and I see it all the time. I have seen it in every system I have ever been involved with, dealing with technicians who whether they're factory trained in their product or just hobbyists, it doesn't matter. It's a common fault of novice technicians, the uninitiated, let's say. Don't guess at what the problem could be. A lot of times somebody will sit in front of a piece of equipment, it's not working, and they go, well, maybe it's this, and they'll start poking with something, and then say, well, maybe it's that, and they'll start poking with something, and they do maybe, and you can do maybes forever. This is my rule. Call it, Mark's rule or whatever. The number of things in any given system, the number of things that can be wrong are like it's like a geometric square. You can multiply things by all of the factors that are required for the device to function properly. And you can play maybe it's this, maybe it's that for a long, long time and never find the problem. The quickest way to determine what's wrong with any system is to go down the list of what is required for that system to function. It's a much shorter list. By leaps and bounds, it is a much, much shorter list. And yes, it's kind of boring and it's kind of simple, and it may make you feel as if you're not the brilliant, tactician that you'd like to think you are, or technician or whatever. But it is a very effective tactic. Start with, is it plugged in? If I have an external power supply, is my power supply giving me the proper voltage? Is that voltage reaching the radio? Do I have a wiring problem? You know, just are all the wires energized? This thing here that I showed you before, this has 4 wires. Well, what if one wire is open? Let's say one positive leg is open and the 2 grounds are good. It's 2 grounds, 2 hots. And that leg isn't quite carrying the current you need. So you key the radio, it works fine in receive, and you put it in transmit, and it gets kind of squirrely and wacko. And gee, what the heck's the matter? You got this voltage drop across the one wire. Or maybe power's not being distributed evenly in the radio because you've got one wire bad. So do you have power? Okay. After that, I like to find in any of these devices, almost all of them have in it what I usually call the AVR board. Is the voltage regulator board. One location, whether it's part of the power supply or separate from the power supply, often separate from the power supply, there'll be one board that will contain a bank of regulators. So you'll have maybe 1 or 2 regulators for 8 volts, which they tend to like to use for switching. You'll have 5 volts. Obviously, if there's logic in the radio, there'll probably be 5 volts. Now the newest stuff is down to 3.3 volts. You might have a 3.3 volt regulator. And you'll have a number of voltages in the radio that will be labeled with a T or an R. You know, TXB, RXB, which are switched. So are those voltages there? Are they correct? And they're easily found. They're going to be on the pins of some header on the board. You know, look at your schematics. Look for those. If you have a service manual, a lot of times they'll outline all of those lines in red, which is very convenient. Okay, so do we have power? And so far, all we're using is a voltmeter. Very simple. If you have access to an oscilloscope is fine. I like an oscilloscope. I've just become very accustomed to an oscilloscope. I never trust meters, especially digital meters. I like analog meters. I use digital meters for setting specific values where I need to see, you know, 13.800000, you know, it's where I need a real specific number accuracy. Yeah, I'll use a digital meter. But for just general troubleshooting, I like to see, is my voltage wavering on a meter, and I'm really an oscilloscope guy. I like the oscilloscope. I like the very high impedance, you know, 10-to-1 probe, and I just, you know, go poking around. And you get to see all kinds of other things, like, is there noise on the line? You know, some of these radios will simply not function right if an output capacitor on a regulator is bad. Usually on these little 3-terminal, 4-terminal regulators, you'll have like a 1 microfarad electrolytic on the output side. I've seen them go bad. And the output of the thing will be negative. You put an analog meter on there or digital meter on there, and you'll see an average of 5 volts. It looks fine. You put a scope on there, and you see 5 volts plus or minus some sort of oscillating signal that could be as much as 2 volts. A lot of stuff's not going to like that. Not going to work with that. You got a bad output cap on a regulator. So simple stuff. Do you have power? Do you have power, and is it correct? Both to the radio and inside the radio. Okay. So go down the list of what do you need. After that, you have basically, what is a radio? It's oscillators and mixers. Oscillators, mixers, and amplifiers. I'll amend that. So are your oscillators there? Are they operating at the right frequencies and the right levels? Do you have first local? Do you have second local? If you have local oscillators, and what frequency are they at? Moving on, do we have mixer action? Is the mixer developing an output? Now, here's where it gets to become a little tricky if you don't have certain kinds of test equipment. Mixers are always going to, well, No, I shouldn't say always. Balanced mixers won't. But anyway, generally, mixers will always display quite a bit of their fundamental inputs. So meaning F1 and F2 will be very prevalent. I mean, you'll have lots of F1 and F2 at the output of a mixer. The product that you desire, which is F1 minus F2 and F2 minus F1 and F1 minus F2, you know, is whatever, plus and minus. All of those products are going to be selected for in following stages. So if you go directly to the output of a mixer, if you see anything at all, usually one of the inputs is going to be significant. That's primarily what you're going to see. You're going to see either F1 or F2 in predominantly. So if the output of your mixer is supposed to be 455 and the input is 8.33 and whatever 9 roughly, don't expect to see 455 in the output. But if you go one or two stages beyond that, yes, then you should definitely see 455. All right, so do I have oscillator input to my mixers? Do I have output from my mixers? And at that point, if you're like troubleshooting a receiver, obviously you probably want to bring up a signal generator and put a signal into the radio. Don't use the antenna for a signal source. Don't listen to noise on the air and try to get an idea of what's going on with the radio. Use something that's a little bit more stable. And what I used to do, I used to cheat before I had all of these fun toys up here. I used to cheat, and I used to generate signals for tuning up VHF, UHF stuff by using the local oscillator of a scanner, and simply tune the scanner to either 455 or 10.7 above or below the desired frequency, depending on how it worked. But usually you can program a scanner above or below its IF, and the local you'll get enough leakage from the local oscillator in the scanner that you can plug it into the back of the radio, and you have a pretty stable test signal. May not be the level you want, but it's stable and it's there, and you can hear it, and you can tune off it and heterodyne it and all that. That's kind of nifty. So yeah, you need a test signal would be preferable. If you don't have a signal generator, you can use the harmonic of just a dirty oscillator. Make yourself a little single transistor crystal oscillator, plug a crystal in there, and tune to a harmonic of it. It'll be there. You'll find some signal. But signal generators are nice to have. Even a cheesy one that floats around. I don't have any cheesy ones anymore. I've sold them off or given them away. But I've had some of the simpler ICO and what was it, Sencor, and there's a whole bunch of them that I've had, and they work. I mean, they generate a signal. They're not, calibrated. They're not stable, but they work. All right. And marker generators. A lot of the radios have markers in them. I mean, just turn the marker on. That's an excellent source of signal. Just troubleshooting receivers. Okay, so my point is, look for things that should be there. So after that, you get into more detailed troubleshooting, like looking at voltages. And when you look at voltages in circuitry, a lot of times it's damn near impossible to gain access to a circuit point or to have a reference. I mean, even with a service manual, they're not going to give you all the data that you might need. So here's where you need to use some common sense. You need to look at a circuit and you say, well, gee, if I have a transistor and it's a common collector amplifier, voltage amplifier, and it's being fed with 12 volts through a resistor, then I should probably see maybe, I don't know, 6 volts, 8 volts, something like that at the collector. And if you do, then you can assume that that transistor is probably biased on and functioning. Some RF circuits, you won't see that because they'll feed the collector through a very low impedance device like a choke, like a little inductor. So you will see, you know, B plus will be all the way up at like 12 volts. So then you go to the emitter, and usually there's a little feedback resistance on the emitter to ground, you know, maybe 100 ohms or 1,000 ohms or whatever, and you see a little voltage there. Okay, that transistor's biased. Move on. Don't worry about the specifics. I have rarely, if ever, found the voltages stated in the service manual or on a schematic are accurate. They're close. Plus or minus 50% is not unusual. You know, if something specifies, oh, we should have 3 volts here, and you put a probe on it, and it's 2.1 or 4.2 or something like, it's around 3 volts. Really, there's that much variation in these circuits. There shouldn't be. Ideally, engineers should design their bias circuits so that they are more self-stabilizing to accommodate for changes in device gain, but they're not. And, you know, they could be all over the place. Some brands are worse than others. I won't say which. You can find out for yourself. I will get all kinds of hate mail if I start telling people what I like and what I don't like. You might find out, though. It'll slip at some point. Let's see. So look for what should be there. It's boring, it's tedious, but you know what? You'll get through it much quicker. You will be able to go to lunch saying, okay, now I know what's wrong. How am I going to fix it? What do I need to fix it? As opposed to coming back from lunch and saying, oh, what the hell's wrong with this thing? Trust me. Look for what's wrong. Look for what's required, not for what's wrong. It's a much shorter list. Lastly, static protection. Now, if you live in the Everglades, you can pretty much ignore what I'm going to say. You know, maybe the Louisiana Bayou somewhere, you can get away with it. But if you basically live anywhere else in the country, static protection. Ground your equipment. Ground what you're working on before you open it up, before you get your hands in it. And what's going on here? Here we go. And ground yourself. This is a wrist strap. It's much like a watch band. Actually, I think this is a Spidell watch band. It's been resurrected several times in its life. Okay, so it's a metal watch band. After wearing this for a few hours, you're going to get a little, body moisture underneath the band. It's going to make really good contact, and you don't want to electrocute yourself. So it has to be resistive. How much resistance? Anywhere from 100K to 10 megohm, but certainly at least 100K. It takes only 5 milliamps of current across your chest to kill you. What the average resistance of the body is varies greatly, but I can tell you when it's salty sweat, it's a lot lower. So yeah, this is, I have a 1 megohm resistor in this lead. See, lead. I have a 1 megohm resistor and a clip lead, and I have a little ground clip on my electrical source, and I test that regularly, make sure I have good grounds here everywhere, and make sure you're grounded. I'll tell you a little story, incidentally. Good friend of mine brought me an ICOM, nice 756 Was it a Pro? I think it was just 756. And brings me the radio, and I'm going through it, and I'm about to make some modifications. Radio was working fine. There wasn't a repair job. I was about to make some modifications, and I noticed on the back of the main board that there was a number of broken connectors. Not uncommon. Don't transport, here's another rule of thumb, don't transport your radios with things connected. You got plugs and wires and cables and jacks, take them out. You're going to carry it around, you're going to move it, take them out. Take the wires out. That's how you break connectors on boards. So I noticed that there's a number of connectors on the back of the board that are indeed broken. The solder joints are broken. Board's not broken. Connectors are okay, but they're not making contact. The solder's broken away out of the board. So all right, let me just zip this board out and fix this up, solder these connections up, put it back together. And it was in the summertime, and it's usually fairly humid down here. I usually actually have the humidifier going, the dehumidifier. I put the radio all back together, and I've got no display. No display. What the hell could be wrong? So, make a long story short, I go through the radio, and it turns out to be there's one tiny little 8-pin surface mount chip, little tiny flat pack, eighth of an inch square, if that much, with 8 leads on it. And it's a dual inverter. It's a pair of digital inverters, and it was being used solely as a crystal oscillator. To the inverter was had a crystal across it, and that was the clock for the video processor. I guess the GPU. And okay, well, gee, that's thank God it's not some proprietary chip that I can't get. It's just a little two-gate oscillator, two-gate inverter. So I look it up, and it's an obsoleted part. Nobody in the States has it. Not Mauser, not Allied, certainly not ICOM. Nobody has this little chip. I can't find this stupid little chip. It's a stupid little 2-gate inverter. I can't find it. It took me 2 years to find it. I finally found a vendor from China that had glommed a stock of these things and was willing to sell me less than 10,000 pieces. This is the problem we have with manufacturing in the United States, but I'm not going on to that. These vendors want to deplete their inventory. It's costing them money. The government's taxing them on it. They're not selling the parts. Nobody wants them. Get rid of them. They sell them off to China, who's got lots of warehouse space and will eventually sell it back to us at 10 times what they bought it for. So I did find a vendor that was willing to sell me 10 pieces. So I now have 10 of these little oscillator chips should I ever need them again. But here's the kicker. It took me 2 years. And I would be like every couple of weeks, I would be back online. I had all kinds of feelers out. Alibaba kept sending me messages for 10,000 pieces. Yes, I got the chip. I put it in. The radio's working. 2 years later. Did I learn my lesson? Absolutely. Am I really careful about static? 99.9% of the time. Was I careful enough this time? Obviously not. And I learned my lesson. So please, don't fool around with static. Make sure you bring everything to the same potential. Touch the chassis, touch the boards. Before you take a tool and stick it in there, make sure you're discharged. Oh, where is it? I don't see it here. Somewhere here I have a can. Maybe it's empty. I might have used it all. Static guard. I want to say cling free, but that's a dryer sheet. There's a product called Static Guard, and I think it came out in the 70s, and The disco girls used to spray it on their polyester skirts all the time so that their skirts wouldn't stick to their hose and ride up their backside, which was kind of cute, but you know. Anyway, static guard. It's in, I think it's an ammonium salt. It's an organic ammonium-based sulfide salt. Anyway, it works really well. I spray it all over the place because I have carpet in my radio room here, and yeah, I can generate some static. So there's lots of, although I don't know, this carpet's so dirty and damp these days that maybe not. So yeah, grounding. I'm not going to get into talking about, you know, power sources. Obviously, you should have, you know, properly fused power supplied to your work area, and don't cut the ground connections off of your devices. A lot of people would say, oh, don't use a grounded soldering iron because you can short things out, or that's a crock of horse feathers. If you're using a soldering iron, the device shouldn't be powered up. There's no problem with using a grounded soldering iron. I don't know if there's any problem using an ungrounded soldering iron, provided that it's, you know, static discharged. I mean, that's easy enough to do. Just touch it to the chassis. Bring everything to the same potential. Can you get everything to zero? Maybe not. But if everything's at the same potential, you know, you shouldn't have a problem. But it's those little charges, it's those little things that'll kill you. Something as simple as, I'm sitting in a chair here, and something as simple as spinning around to answer the phone and sliding my feet across the carpet and then spinning back, I can pick up an incredible charge. And you know, I moved my feet 10 inches, but I was away from the bench. Whatever I did over here at the desk, I was away from the bench. I've built up a charge. Grounding, static. Okay, so I think that's enough of my BS for the moment. Maybe I can edit some of this crap out. Let's get into this radio.